All right, welcome to today's explainer. Look, for the next few minutes, I want you to consider me your lead systems engineer, and you're my apprentice. Because today, we aren't just, turning wrenches or talking about basic car maintenance. We are going to completely tear down our everyday assumptions and reveal the ultimate technical manual for building an immortal, million-mile 2023 Toyota Corolla. We're stepping completely out of the standard consumer mindset and jumping right into high-level systems architecture. To pull this off, we have to use a conceptual framework called synoptic optimization. Now, this isn't just a car thing, it's a universal problem-solving philosophy. What it means is that we absolutely abandon the idea of isolated single metric tweaks. Instead, we map out the hidden dependencies across thermodynamics, fluid dynamics, and material science. We are building a closed, highly resilient system, and we're going to use this exact lens to completely change how you perceive mechanical fragility, literally transforming a standard commuter car into a fully self-reliant transport node. And the foundation of our entire project really relies on one core truth. Here's the catchphrase I want you to burn into your brain. What you're observing isn't wear, it's energy transfer. Seriously, when you shift to a synaptic lens, it permanently changes your perception of mechanical failure. An engine doesn't just break down because it gets old. It fails because it exists in a dynamic tension field of energy and material flows that we just haven't properly insulated. Once you really grasp that, you can out-engineer a trillion-dollar consumer market that's essentially built on planned obsolescence. So, here's our technical syllabus for the day. We'll hit the vulnerability matrix, then the infinite fluid loop, move into cryogenic powertrain fortification, tackle kinetic and aerodynamics, and finally wrap up with the million-mile return on investment. All right, diving right into Section 1, the vulnerability matrix and engineering dependency. As your mentor, the first thing I need you to understand is that standard factory maintenance is inherently fragile. Why? Because it's built entirely on dependency. Modern engineering has basically traded away autonomous margins in exchange for extreme performance efficiency. Think about the structural parallel to agriculture. The Green Revolution bred these amazing high-yield crops, right? But they cannot survive without a continuous, centralized stream of synthetic fertilizers. Well, the modern auto engine follows that exact same systemic trajectory. Early, low-stress engines were incredibly durable by design, but today's performance-focused power plants? Totally different story. To meet strict fuel economy standards, engineers dropped oil viscosities down to water-thin 0W16. This forces the modern engine to operate in a highly dangerous boundary zone, where metal surfaces are literally trying to collide. To prevent the engine from destroying itself, it is completely reliant on extreme pressure chemical additives like zinc. Without that centralized chemical scaffolding, the whole system just collapses. Which brings us to Section 2, the infinite fluid loop and bypass filtration. So how do we solve this vulnerability? We basically take the industrial logistics used in commercial aviation fleet management and long-haul semi-trucks, and we shrink them down for our passenger car. You see, you can't safely reconstitute used synthetic oil at home with standard garage tools because the chemical additives get destroyed. But the synthetic base oil molecules themselves, they are virtually indestructible under normal heat. So we install a continuous bypass filtration system. Here is your step-by-step checklist for a weekend project. First, safely divert about 10% of the oil flow using a sandwich plate. Second, push that oil incredibly slowly through an ultra-dense 2-micron cellulose or microglass matrix to scrub out all that microscopic metal wear dust. Third, chemically trap any moisture before it can form harmful acids. And finally, return the oil to the pan without restriction. Just remember, and this is absolutely crucial, you must use strict safety protocols when handling and routing those high-pressure braided PTFE oil lines to prevent catastrophic oil starvation. Let's look at the actual math here, because the financial and resource savings are striking. By shifting to a continuous bypass strategy, you transition away from a wasteful drain and fill model to an infinite use management strategy. Instead of blindly relying on a little mileage sticker on your windshield, you verify your oil health with an annual fluid lab analysis. Over 5 years, your operating cost drops to just $115 a year compared to standard factory maintenance. More importantly, we can really contrast the incredible efficiency of this synthetic oil management against the massive limitations of conventional oil recycling. With this setup, a stockpile of just 70 quarts of synthetic oil guarantees you 700,000 miles of pristine lubrication security. That's insane, right? Moving on to Section 3, cryogenic powertrain fortification. Okay, this is the core material science of our build. We must fundamentally alter the engine's internal lattice structure. We have to eliminate parasitic drag and structural fatigue from the inside out. -300 degrees Fahrenheit. That is the magic number. We aren't just adding chemical coatings here. We are utilizing deep cryogenic tempering. By plunging the bare structural steel and aluminum components down to -300 degrees for a multi-day soak, a profound metallurgical change happens at the molecular level. The metal's soft, irregular, retained austenite structure is permanently converted into ultra-dense, uniform martensite. What does that do? It relieves residual manufacturing stresses, creates an atomically flat, low-friction surface, and essentially makes the metal forget how to fatigue. You analyze the failure points, you eliminate them, and you minimize that boundary zone friction. This alone can bump your fuel yield from 32 up to 34 miles per gallon in the city. Now, what does this level of industrial logistics actually cost? Because non-metallic parts can't be frozen, the entire powertrain must be completely stripped to bare metal. Surprisingly, the lab fees for the cryogenic soak are pretty accessible, around $1,000 to $1,400. But Phase 3 is where the logistical risks and the total investment really become clear. You're estimating exactly 64 to 78 shop hours. Why so many? Because cryotreatment slightly alters the crystalline density of the metal, meaning you face the critical task of micro-measuring oil clearance tolerances down to 10,000ths of an inch before you can even think about engine reassembly. So the total bumper-to-bumper retrofit investment runs roughly $10,000 to $14,000. But listen, as your mentor, I'm going to give you an industrial fleet strategy right here to bypass those high shop costs. Do not immobilize your daily driver. Instead, acquire a clean, low-mileage donor engine and transmission. Strip them down to bare metal on your own time, right in your own garage. Send them out for the cryogenic process, and then precisely reassemble them on a stand into what we call a 0-hour reserve power module. When you're absolutely ready, you execute a rapid 48-hour weekend hot swap. You minimize your downtime, drastically cut those labor costs, and you achieve lifetime systemic reliability that factory standard replacement components just can't touch. All right, Section 4, Kinetic and Aerodynamics. So moving outside the engine block, this phase is directly comparable to aerospace boundary layer management. Let's map out the energy density trade-offs of braking between factory stock components and our custom parts. A purely mechanical Kerr system, like a high-speed flywheel, is incredibly efficient at returning raw kinetic energy, but it loses that energy super rapidly over time due to friction. On the other hand, standard magnetic regeneration, like what you find in hybrid Corollas, stores energy long-term in chemical lithium-ion batteries. But those batteries can absorb the instant high-amperage rush of a hard brake without suffering thermal shock. The solution? A hybrid energy storage system. By wiring a bank of electrostatic supercapacitors directly into the loop, you capture 95% of that massive kinetic braking spike instantly, which perfectly buffers and protects the main chemical battery. And we have to manage atmospheric friction just as aggressively as we manage internal energy. To reduce aerodynamic pressure drag without paying a massive skin friction penalty, we use mesoscale surface texturing. By utilizing advanced resin 3D printing, we can create microwave channels, we call them riblets, that are just 20 to 50 microns wide. These microscopic grooves trap stagnant air inside their valleys. So when high-energy turbulent vortices hit your car, they are forced to slide over this dead fluid cushion rather than grinding directly against the solid metal. Combined with active vortex jets at the rear roofline, we fundamentally re-engineer the car's atmospheric envelope. Finally, Section 5, Future Materials and the Million-Mile ROI. So, how do we evaluate the systemic maturity of an apprentice's project like this? We have to ask, does this extreme mechanical resilience provide genuine financial value? To ensure our million-mile vehicle is completely self-sustaining over the next 30 years, we have to look beyond current mechanical limits, specifically at things like tires. Traditional vulcanized rubber sheds permanently, right? But over the next decade, emerging self-healing biopolymers are going to absolutely revolutionize tire design and sustainability. We're talking about reversible disulfide cross-linked polymers that literally heal their own bonds. Airless tires utilizing living photosynthetic moss to capture carbon, and even sequence-defined DNA origami scaffolds used to program a regenerating synthetic chain. This is exactly how self-healing materials will impact car maintenance in the near future. Let's bring it all home and summarize the specific technical trade-offs between a short-term component investment and your lifetime systemic resilience. A complete cryogenic powertrain retrofit, even at its absolute highest estimated cost of around $13,500, really pales in comparison to the $25,000 to $30,000 hit of buying a brand new replacement vehicle.
By pre-staging a cryo-treated reserve module and running a continuous bypass loop, you can compare the lifetime ROI of a total cryogenic retrofit versus a factory replacement. And the math just always wins. You don't just save money, you completely bypass the new car consumer market entirely for 3 decades. You transition from a vulnerable consumer into an autonomous, closed-loop transport node.
Which brings us to the end of our explainer. My final thought to you, my apprentice, is this. Synoptic optimization isn't just about car parts, it's a universal grammar. When you stop viewing the world as static consumer objects and start seeing interconnected thermodynamic systems, what complex infrastructural problem will you solve next? Hold on to this conceptual framework, apply it to literally everything you engineer, and never accept the artificial boundaries of modern specialization. I'll see you next time.